right, welcome back to the third video on electrokinetics. We're going to be talking about statistics and curve fitting. So, right off the bat, I'm going to be challenging the most common method for fitting kinetic parameters using a TOEFL analysis, and I'm going to make some suggestions of things that are more sound statistically. So, the common method is to get our linearized Butler-Volmer equation. And then how we're going to linearize our data is we're going to plot our overpotential and the natural log of the current. We'll fit a straight line to the extremes of the curve, so very positive overpotentials and very negative overpotentials. And then we get the slopes of these lines, the intercepts of these lines, and then from those, we calculate out the transfer coefficients and the exchange currents. And I believe that this method was very popular for a while because we didn't have computers. So a lot of this analysis being done graphically. And, graphically, it's nice to get slopes and intercepts from straight lines. But now that we have computers, we can use the full expression. And statistically, this is more sound because whenever you linearize data, you make these standard deviations in your data non-uniform. And what that does is it essentially makes it so that your data will preferentially fit onto some portions of your data, but not to all of them. And this is unavoidable whenever you linearize an expression and try to fit data to the linearized data. Instead, from a statistical standpoint, it's much more sound to fit data to the data, fit a curve to data that hasn't been transformed yet. And so my first suggested method is just to use the full non-linearized expression for the Butler-Volmer equation and fit it with a sum squared error minimization. So that's my first suggestion. And then as a second suggestion, you could fit the really high over potential data, the very negative over potential data, like with the linearization method, but just don't linearize it. Just keep it in its exponential form. And so let's walk through some examples. I did all of these methods, and we can see how well our fits match the data. So there'll be two linearized fits, and these are fits with the cathodic and the anodic data. Same here, we're going to have cathodic and anodic data with the non-linearized forms at these potentials, and then we'll also have the full Butler-Volmer expression fit to all of the data. So if you'll note here on this TOEFL diagram here, we have the natural log of current, we have the overpotential here, and here you can see the range of data that we're fitting to. And it's equal for both the anodic and the cathodic sides. The data is in black dots. So cathodic, this is non-linearized, that would be in blue. Anodic, non-linearized in orange. And then green, we have the linearized cathodic fit, and in red, we have the linearized anodic fit. And remember, my advice is to not linearize your data because when you look at the residuals or the difference between your fit and your data, you always, or at least on a statistical average, will have worse fit data for your linearized expressions than for your non-linearized expressions, and especially then from the full data. So as you can see, for residuals, what we're looking for is if your residuals are equal to 0, well, then that would indicate that there's no difference between your data and your fitted expression. So your predictions are right on. And what you'll see here is that we go from linearized data to non-linearized data to just fitting the full Butler-Volmer expression. Here we can see the TOEFL diagram essentially unTOEFLized. So we're just plotting the current versus the overpotential. And you can see here that, the same trend continues, right? The data is best fit using the full expression, and if you're not going to use the full expression, at least don't linearize your data. So this analysis was done with a transfer coefficient of 0.5 and an exchange current of 1 microamp. I will note there is a reasonable amount of noise built into this data. And so, it's not just like I'm fitting the full expression to perfect data. There is some noise here. Here we can see that, this holds when we change the transfer coefficient as well. Though you'll notice that changing the transfer coefficient away from 0.5 impacts different. It impacts the cathodic fitting and the anodic fitting differently. But all the trends still stay constant. Our worst fits are linearized, and our best fits are non-linearized or the full fit. Of course, it holds when we switch back our transfer coefficient the other way as well. So why did we linearize? Like I said, it was very handy prior to broad access to digital computing, but now we have that. And the reason why it changes your data is because when you linearize, you're changing the variance and not uniformly. And fundamentally, that changes how we need to analyze things statistically, and it just gets, fitting things after you've made that change makes it so that your fit will prefer some parts of the data over others. So parameters that are fit through linearization are always more likely to be incorrect than those fit with non-linearized or with the full data set, the full Butler-Volmer expression. So here are my 2 questions. Will you ever linearize your data to fit parameters again? And what if it's not an electrochemical context? What if I'm not fitting the Butler-Volmer equation? What if it's something else that I'm fitting? And, usually I have you stop and answer these questions on your own, but I'll tell you the right answer. The right answer is no. Just don't linearize your data. There's no need to now. We have computers that can solve a little bit more complicated problems for us. We can do sum squared error minimizations rather easily. Microsoft Excel can do this. Any kind of programming language can do this. So there's my little spiel, and play around with it and see what kind of a difference do you see if you linearize your data versus not linearizing your data. And I think you'll come to the conclusion pretty quickly that you shouldn't be linearizing your data. All right. We'd love to invite you back to watch our last video in the lesson on electrochemical kinetics as we cover a few other kinetic concepts. Thanks.